Welcome to this presentation covering Section 3 of the EI Guidelines for Avoidance of Vibration-Induced Fatigue Failure in Process Pipework. We will discuss how proactive assessments help operators prevent failures, reduce risk, and support safe and reliable operation. Purpose and scenarios for proactive assessment. Proactive assessment is a structured methodology designed to identify and mitigate vibration-induced fatigue risks in process pipework before failures occur. It is applied in three primary scenarios: number 1, when designing a new process system; 2, when assessing an existing plant; and number 2, when evaluating changes to an existing plant such as operational or equipment modifications. Each scenario shares common steps but differs in sequence based on available data and project stage. For new designs, emphasis is placed on paper-based assessments during the design phase to incorporate mitigation measures early. Existing plant assessments often begin with visual inspections and targeted vibration measurements to identify immediate threats. For plant modifications, the assessment integrates with hazard or HAZOP processes to ensure changes do not introduce new vibration risks. This proactive approach contrasts with reactive strategies that only address issues after failures occur, thereby reducing downtime, improving safety, and minimizing costs. The methodology ensures that vibration considerations are embedded throughout the life cycle of the plant, promoting reliability and compliance with industry standards. Proactive assessments integrate design review, analysis, and field inspection to identify vibration-related risks before failures occur. The procedure adapts based on whether the system is new, operational, or undergoing modification. A proactive assessment is applied in three common scenarios: number 1, new system design; number 2, assessment of an existing plant; number 3, assessment of modifications to an existing plant. Each scenario uses similar steps but in a different order depending on what. Why proactive assessment? Rather than reacting to failures, a proactive framework allows for systematic identification of risks throughout the asset life cycle. This reduces unplanned downtime, enhances safety, and minimizes cost. Why proactive assessment required? A proactive approach ensures early identification of excitation mechanisms, ranking of systems by likelihood of failure, LOF, prioritization of resources to high-risk systems, integration of vibration risk into design, inspection, and operations. Proactive assessment scenarios. Each case involves identifying potential excitation mechanisms and evaluating their impact on structural response, but the sequence of activities differs. Scenario 1, new design, focus on paper-based engineering assessment, identify issues before construction, apply good design practice early. Scenario 2, existing plant. Begin with visual inspection and vibration checks, review operational behavior and as-built conditions. Scenario 3, plant. Modification, assess changes that may alter excitation mechanisms, integrate with hazard or HAZOP processes. Understanding likelihood of failure and risk matrix. Risk assessment and proactive vibration management combines two key elements: likelihood of failure, LOF, and consequence of failure, COF. LOF is a conservative screening metric calculated using simplified models to rank systems based on potential excitation mechanisms and structural response. It is not an absolute probability but serves as a prioritization tool. COF, determined by the user, reflects the impact of failure on safety, environment, and business continuity. Together, LOF and COF form a criticality matrix that categorizes systems into risk zones, guiding resource allocation and corrective actions. LOF scoring applies to main lines, small bore connections, SBCs, and thermal wells. Considering factors such as flow-induced turbulence, pulsation, mechanical excitation, and surge events. Systems with high LOF and high COF require immediate intervention, while those with lower scores may only need monitoring or minor adjustments. This structured approach ensures that vibration risks are systematically evaluated and managed across all operational scenarios. Failure mechanisms consideration. Although fatigue is the main focus, fretting and transmitted vibration can also lead to loss of containment or component damage. Proactive assessments evaluate risks from fatigue cracking due to vibration, fretting wear, structural resonance, transmission of vibration between lines. Main steps of proactive assessment, qualitative and quantitative assessment process. The proactive assessment process consists of 4 main assessment methods that these steps will explore more detail in the next slides. Number 1 is qualitative and quantitative steps. The assessment combines qualitative identification of risks and quantitative calculations for excitation mechanisms. These steps will explore more detail in the next slides. Number 2 is inspection and measurement. Visual inspections and vibration measurements validate assumptions and classify vibration severity levels. Number 3 is specialist analysis techniques. Advanced methods like dynamic strain measurement, modal analysis, and predictive modeling address complex cases. Number 4 is corrective actions and verification. Corrective measures reduce risks by modifying excitation or increasing stiffness, followed by verification inspections. The assessment process main steps consists of 9 main steps. Number 1, qualitative assessment to identify potential excitation mechanisms and rank systems by risk. Number 2, quantitative mainline LOF assessment to calculate LOF for each excitation mechanism such as turbulence, pulsation, and surge. Number 3, quantitative SBC LOF assessment focusing on geometry, span length, and location of small bore connections. Number 4, quantitative thermal well LOF assessment to evaluate susceptibility to vortex shedding. Number 5, visual inspection to capture as-built issues and validate assumptions. Number 6, basic vibration measurements. Number using RMS velocity criteria to classify vibration levels as acceptable. Concern or problem. Number 7, specialist techniques. Number including dynamic strain measurement, modal analysis, and predictive modeling for complex cases. Number 8, corrective actions aimed at reducing excitation or increasing structural stiffness. And number 9, implementation and verification of corrective actions through follow-up inspections and measurements. This comprehensive approach ensures that risks are identified early, quantified accurately, and mitigated effectively, supporting safe and reliable plant operation. Summary and key takeaways. By systematically applying qualitative and quantitative assessments, operators can effectively manage vibration-induced fatigue risks throughout the life cycle of process piping systems. The proactive assessment framework identifies risks early, quantifies likelihood of failure, ensures thorough inspection and validation, guides effective corrective actions, enhances reliability and safety.